There we go. All right, hello everybody. This is Time Series Analysis, MMA 702, and this is Lecture 2. Today we're going to be talking mostly about linear models. So, our first models are named AR, which stands basically for lagged variables, in which the value of the return at a certain point depends on a sort of a stochastic way from a certain number of previous variables. For this small example, we'll pick these coefficients, and we're going to make RT depend of RT minus 1, RT minus 2, RT minus 3, and a shock factor named AT, from which we know that the variance is 0.01. This model is called AR3 because the growth rate depends on the growth rates of the past 3 quarters. If we made it depend on 12 quarters, it would be called a AR12 or whatever. So 3 questions appear from here. First one is pretty intuitive. How do we specify this model with a certain set of data? Second, is it adequate for the data? And three, what are the implications? What limitations do we have? Uh, is, is it possible that there are better models? Well, we will see this. Now, here we have a US quarterly growth rate of real GMP, 1947 to 1991, in several different plots. Now, in order to get a better grasp of how AR models work, I'm going to be working with AR1 models first, in which we are picking up our growth rate as a variable of the growth rate in the previous period and a shock factor. Here we have two coefficients, phi sub 0, phi sub 1. They are real numbers. We'll call them parameters, and we have to estimate them from the data. An example, this is a AR1 model. These models are stationary if and only if the dependence of on RT minus 1 is lagged with a coefficient that is smaller than 1 in absolute value. The reason why this is as it is if it would be greater than 1 or equal to 1 or to minus 1, we will never get stationarity. The thing is, this is the model is some sort of strings in a sense. The mean of an AR1 model is phi sub 0 divided by 1 minus phi 1, and if we call that mu, we can see that the model becomes something like this. RT minus mu is one coefficient that multiplies RT minus mu and the shock factor. This model also has two parameters, but this one is different. It explicitly uses the mean of the series, and well, this is less commonly used in books. You'll probably not find it. It is in the textbook of this course, however. But this is the model representation used in R, so it's always easier if you give it mu and phi sub 1. Variance of this is variance of the shock factor divided by 1 minus phi 1 squared, and the autocorrelations are pretty straightforward. Rho sub k is phi sub 1 to the power of k, and here is where you see why stationarity depends on that absolute value being smaller than 1, because when you elevate this that is between minus 1 and 1 to greater and greater powers, this goes to 0 pretty fast. But if this is greater or equal to 1 in absolute value, this can go to infinity, so we have a potentially infinite autocorrelations. Now, let's suppose we have our forecast origin, and for simplicity, we shall use model representation in 1 and define our xt as r sub t minus mu. This is not r sub mu. This is r sub t minus mu. Okay, in this way we can rewrite the model, and it becomes like this. So here, forecast of RT is mu plus forecast of xt, basically. So if we go for one-step forecast at our certain time on our origin n, this xn at one step would be phi sub 1 times xn, and the error would be, we will call it e sub a, will be xn minus 1 minus the xn1, this excuse me, but I'm hearing something. Okay, yeah, I'm sorry, but the Google Assistant just interrupted me. For some reason, we summoned it accidentally. So, one step ahead forecast error is the corresponding data minus the estimate we did with our model. Oh, and this is exactly equal to a and my n plus 1. This makes a sub n plus 1 the unpredictable part of x of n plus 1. I mean, it's the error. It's something we cannot consider with our model. It's exactly the shock at time n minus 1. That's where I want to where I want to go. The shock part, this cryptic mysterious a sub n plus 1, a sub t, it's exactly the shock or the error, the unpredictable part of our model. This error has its own variance, and that's sigma sub a squared. If we go two steps ahead, we have phi1 squared times xn for our estimate, and if we go for the error, it will be the same, x1 minus 2 minus the estimate we have made with our model, and that's a shock factor plus phi sub 1 times another shock factor. The variance of this is 1 plus phi sub 1 squared times this, which is always greater than or equal to the variation of the forecast error with one step, because this is always greater or equal than 1. The thing here, what I want to illustrate is that uncertainty in forecast always increases, and this is a perfect reflection of that. So if we take L steps instead of 1 or 2, we have these estimates. This is the error. It's basically a linear combination of powers of phi sub 1 and the corresponding lagged shock values. And the variance is just this sum of powers from, I mean, this will be phi sub 1 to the power of 1, phi sub to the power of 0, phi sub 1 to the power of 2, phi sub 1 to the power of 4, and there we go, times this variance right here. Particularly if L tends to 1, this estimate tends to 0, and so our estimated return goes to the mean. This is called mean reversion. The thing is not only this value converges to its mean, but the variance of this value converges to the variance of RT. This is even more important, because it says that if we're going for long-term forecast, serial dependence is not important. We can just not consider it. The forecast is just the sample mean, and the uncertainty is simply the uncertainty about the series. Now, how can we express this in a more compact way? Well, here it is. Remember that B means go one step behind. Now, one important thing, and a common way to quantify the speed of mean reversion, is half-life. It's defined as the number of periods needed so that the magnitude of the forecast becomes half of that of the forecast origin. For an AWAR model, it's equivalent to this equation. So you can say that x of n after k steps is exactly this, and so we have this equation which we can solve for k because k is a number of steps, and so it's a logarithm of 1/2 divided by the logarithm of absolute value of phi sub 1. Absolute value because logarithm is only defined in positive numbers. And if we have an example, if phi sub 1 were to be 1/2, then k is 1. And if phi sub 1 would be 0.9, then k would be roughly 6.58. Now, the next logical step is to see AR2 models and see where we can find regularities on how to use it or different similarities between them. And so AR2 model is basically defined with this combination. We have a shock factor and we have three factors in independent factor RT minus 1 and RT minus 2. And we can express that as 1 minus phi 1 composed with this go one step behind minus phi 2 with go two steps behind of RT, that's equal to a constant plus a shock factor. Stationarity condition is a bit less simple than the absolute value of phi sub 1 in means 1 and 1. Characteristic equation is this one, and the mean in this case it's again phi sub 0 divided by 1 minus phi 1 minus phi 2. So if we adjust it, we call this move, and we say this. We can write the AR2 model in this way. This is a bit more compact, and if it wasn't the case in AR1 models, because of their simplicity, in AR2 models this notation is pretty handy because it highlights the mean reversion. Of course, only in stationary cases. Regarding autocorrelation functions, phi 0 is 1, rho 0 is 1, rho 1 is this thing over here, and rho sub L is defined in this way for different values of L. Now, if this sort of determinant condition is smaller than 0, then RT shows characteristic of a business cycles. The average length of said business cycles is this thing with this arc cosine stated in radian. If we try to measure this in degrees, we're going to have a really bad time because this won't stop. I mean, this will stop making sense. If we denote the solutions of the polynomial as complex numbers, then we will have 2a is exactly phi 1, and this minus the module of the solution is exactly phi 2. And so k will be equal to 2 pi divided by arc sine of a divided by the module of the solutions. In R, the command mode gives you the module of any complex number, so you can go directly to that. Regarding forecasts, they work exactly the same as in AR1 models. Okay, in order to simulate this in R, I think I don't have the code here, but I will reference that. We can use command ARMA where we only have to give it the coefficients. And now this is for you. Please check autocorrelation functions and partial autocorrelation functions of the above two simulated series. Now, can we express an AR2 model as an AR1 model? Yes. If we expand this problem to R2 and we start working with vectors instead of with the regular real numbers, we have this nice identity. And if we put both equations together, we get we get actually this vector, matrix times vector plus vector, which is pretty well defined. And this is called a two-dimensional AR1 model. Why is this interesting? This is interesting because a lot of properties of AR2 model can be obtained from putting an AR2 model as an AR1 model in this form and using some matrix product relations on that. Now, how can we build an AR model? First of all, we have to specificate some things. First one, partial autocorrelation functions. This is a naive but pretty effective approach actually. We should use consecutive fittings. You can find more details in page 40 of the book. And there's a key thing here, like that partial autocorrelation function cuts off at lag p for an ARP model. I mean, if you go for an AR modeling where you depend on your p previous returns, then partial autocorrelation doesn't make sense if you go beyond because you're not even considered in the model, and that's why. So you might want to check partial autocorrelation functions of the US quarterly growth rate of GMP. Now, another interesting thing, if we consider T to be our sample size, a KK information criterion, also known as AIC of L, is defined in this way. And here, this the sigma sub L squared with a really nice hat is the okay. This word is a bit complicated. Let me check. Maximum likelihood estimate of the residual variance. Now it can be interesting to find the AR order with minimum AIC for all between 0 and P. Now, if a KK information criterion is called AIC, there's another criterion that is called BIC, where in a fraction, instead of putting 2, you put logarithm of t. Now, within the constant term, we check the sample mean. For estimation, we can use either least squares method or maximum likelihood method. I highly recommend maximum likelihood because you need the estimates for AIC in case you use it. And now for model checking, residual is the observation minus the fit, which is basically the one step ahead forecast at each time. And this residual should be close to white noise if the model is adequate. In order to check that, we can use box statistics of residuals, but our degrees of freedom are diminished by the number of AR coefficients. This is actually pretty important. Now we have a beautiful example here. This example, you should actually be able to run from R, like just copying and pasting. But I think I have the R page directly. So for another example, we're going to be checking the monthly U.S. employment rate from January 1948 to February 2017. I used this example to emphasize two things. First one, modeling and prediction using AR models, which includes model simplification, and two, how we handle outliers. Well, first of all, we would get our coefficients here. Our order is set to 11. Sigma squared is estimated in this way. And so we build an ARMA model with this, an AR model with this data. We get the following coefficients from round to 11. Here we have said that we want 11 coefficients. And so we get it Getting this way, the variance of this is estimated this way. Logarithmic likelihood is pretty high. Archaic information criterion is high in absolute value, but pretty low. So we got for the we got to give them names. So here we indicate which columns we want to be considering. Why is this? So we can fix them afterward. So we're going to build another AR model with our data, these characteristics, and these values being fixed, which is pretty important. This is what we call a refinement. We have some coefficients that are all right, so we can actually fix those. Now we summon our model. It gives us these coefficients. The rest are zeros, as we have stated here. Sigma square is estimated as this. Logarithmic likelihood still pretty fast. Archaic information criterion a bit bigger in absolute value. And now for predictions, we get the following time series: frequency 1, okay. Now this emphasizes the importance of refining the method, because here our time series from lower to upper, there is actually a difference. If we would not make this refinement here, situation would be a bit worse, which basically would make our model less accurate, and in some cases, let's say, way less fitting to the data we're using. In this case, the refinement is extremely interesting. Now, regarding outliers, we're going to try and find the minimum residuals to fix those data. So we find the variable with minimum residuals, we fix it, and we build the model again. This is what we get. Logarithmic likelihood is a bit better. AIC is a bit larger in absolute value. Variance is lower. And now we're going to find the variable with maximum residuals, and we're going to merge it with the one we have fixed this way. So we rebuild the model again, and what we see is logarithmic likelihood gets higher, archaic information criterion gets much higher, but variance is shrinking. It's getting lower and lower with each step. So we can see the outlier here. If you go to autocorrelation functions, this is what you get, and these are p-values for your mock statistic. Now, this is mostly it for AR models. I mean, sorry, I blanked out. Yeah, extremely important about this is that you learn these commands to identify which columns you want to be working with, which columns you don't want to be working with, because that can help you. That can help you a lot in refining your models. You can directly cross out some columns, and in that way you create more precise models. You can check for outliers using this, and so that makes it really handy to work with. Now we're finished with AR models. We're going to dedicate some words to moving average models. Moving average models are like kind of complementary to AR models in a sense. And well, main characteristic of this is that it has finite memory. If you go a certain number of steps behind, the model doesn't fit any data really. So we're going to start with MA1 model. It has this form. There's a coefficient theta here, and there are two shock values, two unpredictable things, and a mean. This model is always stationary. The mean or expectation is always mu, and the variance is always defined in this way, with this being the variance of this shock. Now, regarding autocovariance, if you go one step behind, it's defined this way. It's minus theta times the variance times the variance of this is. And if you go more than one step behind, covariance functions are zero, which which basically means that the return in time t is not related to the turn in time in times before r minus 2, r minus 1 actually, r minus 2 will count already. Now, autocorrelation functions, rho sub 1 is defined this way, and of course, if we have already said that bigger correlations are zero, corresponding autocorrelation functions should be zero as well. And so this model has finite memory. MA1 models don't remember what happened 2 time periods ago. Of course, MAN models don't remember what happened n+1 time periods ago. Now, we can forecast one step ahead. And in this case, since the shock value in time a-1 is not known, our forecast will become something like this. The corresponding error would be exactly this, with variance like this. And if we would go to several steps ahead, our estimate would be exactly the mean, which means basically in a MA1 model, multi-step ahead forecasts are the mean of the series. Why? Because the model doesn't have enough memory. The model has as much memory as coefficients you take. So a multi-step ahead forecast error would be defined this way. This is unknown, so it could go pretty wild. And the variance of multi-step ahead forecast error is always this, because it's the variance of R sub t to begin with. So RT is basically a proper linear combination of AT and past observations. Why is it important? It provides a simple way to obtain the shock. You can just move the shock in the equation and put it as a function of R sub t. This makes the model invertible. For an invertible model, the dependence of RT on R in previous moments of time converges to zero, the bigger L is. It makes sense. It has finite memory. The condition for this to be true is that this parameter theta is smaller than 1 in absolute value. And how are they related to AR models? Well, invertibility of MA models and stationarity of AR models are dual. They're not exactly the same, but they're equivalent. So now regarding model MA2, we can write in that way, which makes quite handy this B notation. It's stationary with mean mu. The variance depends on this one, phi1 squared, phi2 squared, and the autocorrelation functions. Rho 1, rho 2 are different than 0, but all the greater order autocorrelation functions are null. What does this mean? It means the forecasts are basically the mean after 2 periods. Now, how can we build one of these? For specification, we will use sample autocorrelation functions. They're all small after lag Q for an MAQ series. I mean, they're autocorrelation functions are 0, but sample autocorrelation functions are small enough, like very small, but there is a way to test them. Constant term, sample mean. For estimation this time, we will do either conditional or exact maximum likelihood. And for model checkings, we will have to use box statistics to check that the residuals are actually white noise. Otherwise, our model doesn't fit well enough, and well, our work kind of goes to the drain. So for forecasts, we will use the residuals as values for A sub t, which can be obtained from the data and fitted parameters. So MAQ models are parameterized by R in this way. I mean, using big stuff here. These theta 1 to theta q are with plus instead of with minus. So we need to take a lot of care in writing down a fitted MA parameter R. For example, if our estimate is minus 0.1 in R, that will indicate that the model is like this. If we were to calculate this by hand, an estimate of phi sub 1 minus 0.5 would turn this minus into a plus. So please be super careful, super careful when working with these MA models. Here we have a small demonstration. We will not be showing ACF plot. So we're going to try and fit an MA1 order here. Using for that order this data in percentage log return. So with this coefficient in hand, our model will be this intercept working as a mean, A sub t, and here this MA1 coefficient. But look at this plus sign. In our theory, it's a minus. So please take a lot of care while working with that. Sigma square is estimated in this way. We have big logarithmic likelihood, and AIC is over the clouds. So we basically don't have to do many improvements. Like likelihood is insanely high in absolute value. It's actually negative, but absolute value is great. And a kike information criterion is incredibly big. So we can build a prediction, and our time series would give us these returns. And as you can see, the first step we have a proper estimate. For the rest, we have the exact same value. And so we have seen that both this AR model is missing out on some things. MA model has small memory, so we can mix both. And in mixing both, we get what I will be calling ARMA model. ARMA model, you mostly want to check ARMA 101 models because it's A, very simple, and B, very useful for generalized modeling. So the form of an ARMA 1 model is basically the best of its house. On the left hand side, it's AR1. On the right hand side is MA1. So in the complete equation will be like this: RT equal phi1 RT minus 1, and this will be the AR1 part. And on the other hand, we have phi 0 plus AT minus phi 1 times AT minus 1. It's stationary as an AR1 model, is invertible as an MA1 model. Remember, if and only if this is smaller than 1 in absolute value, the mean is given in this way. The variance is in the textbook. Please go and check. And our autocorrelation functions are very interesting because Rho of 1 is written in this form, but all the rest of Rho of k's are powers of Rho of 1 times the, sorry, are phi of 1 times corresponding the previous autocorrelation function, previous Rho k minus 1. This is the big difference. And regarding partial autocorrelation functions, they don't cut off after a finite number of steps, which is pretty interesting because it gives more accurate prediction. Now, in order to build that, we are going to be relying mostly on a KK information criterion. We have command auto ARMA from package forecast. Estimation, conditional exact likelihood, you can go for any of them. Model checking, we will do the same we did with MA models. Regarding forecast, MA1 affects the one step ahead forecast, and the rest of the forecasts are similar of AR1. So it's pretty compact. It's really useful and it gives a ton of information. We can write it in different forms. This is the AR form, which is basically an ARN model, and it tells how RT depends on past values. And MA, I'm sorry, I accidentally activated Google Assistant again. So MA representation is written in this form. Here's the average, and it tells how RT depends on past shocks. For a stationary series, this C sub y converts to 0, which means the effect of any shock doesn't affect the model in the long run. Now, MA representation is particularly useful in computing variances of forecast error. Why? Because it's pretty straightforward. Both the error and its variance, they're pretty straightforward if we use the MA notation. Now, this is it for ARMA models. Now I'm going to do some talking about different non-stationary models in the form of a random of, the first one is a random walk. Random walk has this form. Each step is the previous step plus something, plus a shock value. It's basically an AR1 model with this coefficient phi sub 1 that would go here is exactly 1. Now, it isn't stationary because the variance of it diverges to infinity. Why? Because this isn't smaller than 1 in absolute value. It has a strong memory. It has very, very strong memory. Like sample autocorrelation function tends to 1. It goes really, really close to 1. If you go for repeated substitution, we could express this as an infinite sum of a certain coefficient times the shock at a certain point. Why am I using this if all coefficients are 1? Because this gives a parallel with this, which we are very interested in. Why are we interested in that? Because it shows that these coefficients don't tend to 0. This implies that any shock affects the walk permanently. Like there is no way that we go far ahead in time in such a way that the shocks end up not mattering. This case, every single shock matters. Now we can include a drift. We can include a drift in this random walks in the form of the average here. It has a unit root. It's non-stationary. The same reasoning as before. It has strong memory, and it has a tight thread with a slope mu. And it'll be interesting if you can write to me in Canvas and tell me why. Now, regarding the differences, first difference, what you will call, if PT is the log price, PT minus 1 is the log price at time t minus 1, I mean one step before, then the first difference, this PT minus 1 is exactly the log return. Typically, it means the increment of the original series, basically. Now, regarding seasonal differences, if we go S steps back instead of 1, S would be the periodicity. For example, if we were working with quarterly series, then we would take S equal 4. If we were going for monthly series, we will take S equal 12, because that's how many months are in a year. If PT notes quarterly earnings, then Y to T, this seasonal difference, this Y is for year, is the change in earning from the same quarter 1 year before. It's the money you earn this quarter minus the money you earn the same quarter of the previous year. That's why seasonal difference is important. Now, we have some different models, but the constant term means different things. In an MA model, it's the mean. In an AR model, it's related to the mean. Remember that you have to divide it by 1 minus phi 1 to make it work. And the first difference, it's the time slope. Now, regarding practical application in financial time series, you may want to check monthly log returns of General Electrics from 1926 to 1999 in order to get a better grasp on that. Unfortunately, I don't have time to build this example before releasing, but this is a very interesting one. Now, here sample mean is 1.34%. Standard deviation of sample mean is 0.26. It's pretty significant. I mean, that's roughly 12.45% a year, which means $1 investment in the beginning of 1926 is now worth with annual component payment 5,907, with quarterly component payment 8,720, with monthly component payment 9,570. But what if it was continuously compounding? It's a good moment to recall lecture 1, right? So we have talked about unit root. There's a test for that. So we're going to let PT be the log price of an asset. To test that it is not predictable, which is exactly the same as having a unit root, two models are commonly employed, namely both models. Like this one depending only on phi 1, and the other one we'll just add the drift. This is without drift, this is with drift. The hypothesis of interest, our null hypothesis, is that phi 1 is equal to 1, which will turn this into a random walk and this into a random walk with drift. And the alternative hypothesis is that this value is smaller than 1, which will turn this into an AR model, basically. Now, the usual T ratio of the OLS estimate of phi 1v1 is the Dickey-Fuller test. This is called the Dickey-Fuller unit root test or DF unit root test. A T ratio, however, has a non-standard limiting distribution. So now let the variation of PT be PT minus 1. So the augmented Dickey-Fuller unit root test for an ARP model is based on this sum. Look like this is a sum of these differences weighed by this phi y. Here, the P ratio of the OLS estimate of beta, which is the parameter that goes with PT minus 1, is the ADF unit root test statistic. Again, this statistic has a non-standard limiting distribution. So for an example, we're going to consider the log series of quarterly real GDP series from 1947 first quarter to 2009, sorry. Fourth quarter, data from Federal Reserve Bank on St. Louis. It's this data. So we're going to import the corresponding library. If you use the command help, it will show you in the screen the test we can do. We read the table, we build our logarithmic series, and we will run the ADF test directly. We will be lagging it 4 times. So we assume this series has the form of an AR4 model. So title, augmented Dickey-Fuller test. That's what ADF means. So the test says that the lag order is 4. Our statistic is minus 1.7433, and p-value is 0.4076, which that means p-value is greater than the significance value, right? And what do we say if the p-value is greater than the significance value? We have to reject the null hypothesis. We have to accept the null hypothesis. We can't reject it. The criteria to reject the null hypothesis is p-value smaller than significance level. So for more careful analysis, we're going to build this series with the differences on data. We will try to identify an AR model for the series. It's done with this AR command, and so it gives us 3 coefficients. So we can confirm that the difference data is actually, it verifies an AR3 model. Now look at how small sigma squared is. So our previous analysis, this Dickey-Fuller test is justified, indeed. So regarding command ARMA in T, 1, in order to deal with the constant term, if there's any difference, we will use no constant. But we have to consider this subcommand. You might go help parenthesis ARMA and check this. In order to fix these parameters, you will have to use subcommand fix, and it's very interesting that you check how exactly that is done, because it's very interesting, but it's also pretty easy to mess up, really. So I'm gonna drink some water. Now, let's suppose that we have data all the way until time t, and we're interested in predicting RT minus 1. So an intuitive approach says that R sub t should be, it looks like an intuitive approach, that RT should be more relevant than RT minus 1. The possible perturbation, shocks, and everything done closer to our time should be more relevant. Those happened far away in the past. So for a simple formulation, we will assign weight W to R sub T, with W theta, let's call it, yeah, let's say theta is a value between 0 and 1. And so to RT minus 1, we'll give it W theta. To RT minus 2, we will give it W theta squared. To RT minus 3, we'll give it W theta power of 3, theta cube. So we would use theta as a discounting factor. Simple fact. In order to not change the scale, all the coefficients must sum 1. What does that mean? It means exactly this. We take W as common factor, and we have this infinite sum of powers of theta, and it happened to be exactly 1 divided by 1 minus theta. And so this has an interesting implication, and it's that W is exactly equal to 1 minus theta. And so our one step ahead prediction becomes RT plus 1 is 1 minus theta times RT plus 1 minus theta RT minus 1, and all the way. So we're going to call AT plus 1 the forecast error, innovation, or shock at time t plus 1. Then we can build, we can remember this, that there's a predictor and unpredictable part in our forecast, and it will be that way. And so the real RT minus 1 will be our prediction plus shock value. So if we have data RT minus 1, RT minus 2 are interesting in forecasting RT at time RT minus 1. I mean, we're not trying to go into the future, we're going to the past and then back to the present. Then the same argument would show us that RT minus 1, but one step after, I mean, our estimate for RT is written in this way. And so if we substitute, what we have is that our one step ahead forecast for RT, it's actually 1 minus theta times RT plus theta times this prediction. Okay, this is big. What we get is actually RT minus 1 is RT minus theta AT plus AT plus 1. So consequentially, the exponential smoothing model, it's called exponential because of the powers of theta. We can write it this way, which is an ARMA 011 model. We can write it in this way that is super simple, super compact, and very nice to work with. This shows that the exponential smoothing method is simply using an ARMA 011 model with a positive theta, basically. Now, for given discounting rate theta, it's easy to update the forecast using the exponential smoothing method because of the method itself. The method itself says that the one step ahead forecast for RT is a power of RT plus theta times the estimate for RT minus 1, one step ahead, which means it's a weight average of the new data and the previous forecast. So there is it has a really nice way to look into the future. And yeah, this was basically it for lecture 2. I hope you learned a lot. I hope you don't stop moving. Topics for SEM 1 will be chosen when I finish recording lecture 3. They will be up on Wednesday evening. And that's it. Thank you very much for listening to it. Have a nice day, and please stay safe.